that is at the time and so on. Can you do it?
It means always the same, right?
Yeah.
Mr. Gordon?
Yeah, I don't see your
Okay. Hey everyone, very happy to have today our own Jan. So will tell us about indices from the gravitational path integral, new forms of attraction. Okay, thank you very much. So today I'm going to be talking about indices from the gravitational path integral. So this is based on the works done in collaboration with Roberto and Alan, Luca, Samir, and Joaquin. So let me start with the general motivation. So one of the great successes of string theory is reproducing the Bekenstein-Hawking entropy as microscopic counter of states. This is usually done by computing a supersymmetric index in string theory at small coupling, and then comparing it with the area of the horizon of the corresponding supersymmetric extremal black hole in the supergravity regime. The two answers match with each other. However, one could worry that we are essentially comparing with each other two different quantities. On one side, we're computing a supersymmetric index, whereas on the other side, we're computing the area of the horizon, which is supposed to capture the total degeneracy of states for a black hole. It would therefore be nice, for the purposes of studying the gravitational path integral, it would be nice to be able to compute directly on the gravity side supersymmetric indices as well. This can be done using the usual Gibbons-Hawking prescription, in which we compute the partition functions by fixing some asymptotic boundary conditions for the metric and other fields, and then summing over all possible geometries and field configurations consistent with those boundary conditions. So, if you want to apply this prescription to compute now a supersymmetric index, what we can do is we can consider a ground canonical partition function in angular velocity with the value of angular velocity tuned precisely to a purely imaginary value of 2 pi I over beta, where beta is the inverse temperature. When we consider this value of angular velocity, the e to beta omega j in the partition function will end up acting exactly as -1 to the f operator, which acts as +1 on bosons and -1 on fermions. So if we consider such a gravitational partition function with this value, we will directly be computing a supersymmetric index. And this is what we'll refer to as the gravitational index. So the purpose of this talk is to essentially answer the question of what are the finite temperature saddles that compute these gravitational indices in a very general setting of 4-dimensional n equals to supergravity coupled to vector multiplets. Along the way, we'll address a few other questions. So one of those questions will be how do multi-centered black holes contribute to supersymmetric indices in the gravitational path integral? And we'll also discuss a bit about how we can relate the newly found saddles to index saddles in different theories through the so-called M-theory uplift we'll discuss towards the end. Okay, so here's the outline of my talk. So I'll start with the guiding example of Einstein-Maxwell theory. So this is pure n equals to supergravity without vector multiplets. This bosonic part of the action will be given by the Einstein-Maxwell theory. Then following this example, we'll figure out how to generalize this construction to the case of n equals to supergravity with vector multiplets. Then we'll discuss a bit the construction of the multi-centered solutions that contribute to the indices. And then a missing point here, we'll also discuss the 5-dimensional uplifts of these solutions. So starting with Einstein-Maxwell theory, the bosonic part of the action is simply described by Einstein-Maxwell theory. In this theory, the most familiar example of a supersymmetric solution to everyone is given by the extremal Rosen-Nordstrom black hole, which is described by this simple metric. Here, supersymmetry imposes that mass is equal to the charge, and correspondingly, the extremal entropy is given by the area of the horizon, given by pi-QIS split.
Sorry, I'm confused with something.
Yeah.
You're working. I mean, this is not a supersymmetric theory, right? This is just an extremal black hole, but you're working in some supersymmetric.
Yeah. So what I'm considering, I wrote only a bosonic part of the action. So I'm actually considering pure supergravity in 4 dimensions. So in addition, there's gonna be some fermionic chemistry, which I didn't write. And now this solution, which we know just from Einstein-Maxwell theory, it can be essentially embedded in this supergravity theory, and you can check that this solution is supersymmetric. So what it means that it's supersymmetric is that it preserves some killing spinors.
Right, and so I'm trying to connect this with like the whole story of like, you know, the index could give you something non-trivial based on the ground state for all excited states that have to be an equal number of fermionic
Yes,
states, right? So what is the role here of the finite temperature?
So for now I'm just starting with the old Lorentzian story. So here there's no finite temperature yet. This is just like throughout the talk I'm going to be interested in studying supersymmetric solutions. So for that I'm starting for now with just like the known supersymmetric solutions at 0 temperature to kind of get everyone on the same page. And then I'll show how there actually exists a more general family of supersymmetric solutions that are going to be solutions at finite temperature while still supersymmetric. So that's going to be discussed. So this external horizon Nordstrom black hole means a very natural multi-black hole generalization given by the so-called Majumdar-Papapetrometry. It's described in terms of a single harmonic function V and takes the following simple form. For a single black hole in the geometry, this harmonic function will contain a single pole. However, for multiple black holes, it can contain multiple poles. Each pole would represent a single extremal horizon Nordstrom black hole. Importantly, these poles enter the metric as second-order poles. So what it captures is the fact that in the near horizon region for each black hole, there will be an infinitely long ADS2 throat. Now these solutions are good in Lorentzian signature, as they do not contain any closed time curves. However, they are bad in Euclidean signature, because in Euclidean signature we would like to impose, following the Hawking prescription, that the asymptotic time circle is periodic and has finite period beta. However, the regularity of these geometries would require us to actually fix inverse temperature beta to infinity, so we're directly forced to work with 0 temperature solutions. There exists, however, a more general family of supersymmetric solutions in Einstein-Maxwell theory, and these are given by supersymmetric rotating Kerr-Newman black holes. So these are described in terms of the usual Kerr-Newman metric, where supersymmetry imposes that mass is equal to the charge. However, we kept the rotation parameter little a non-zero. Equivalently, this metric can also be written in the so-called in the form of the so-called Israel-Wilson metric, which is analogously to Majumdar-Papapetrometry. It's a multi-black hole generalization of the supersymmetric Kerr-Newman black hole. It is described now in terms of 2 harmonic functions, V and V tilde, and takes the following form, where this one-form field omega E is simply defined through these equations in terms of the harmonic functions. Now, importantly, for this single rotating Kerr-Newman black hole, we actually have now 2 poles in the geometry, which we denote here as the north pole and the south pole. Each of these, like one pole enters the harmonic function V, the other one enters the harmonic function V tilde, and importantly, these poles enter now the metric as first order poles. So what that means is that now in this geometry, in the near horizon region, we actually do not have anymore an infinitely long ADS2 throat. Our geometry actually caps off at some finite distance. Now, as you might have noticed, these solutions, you usually don't see them because they are really bad in Lorentzian signature. What we essentially did was we violated the extremality bound of the Kerr-Newman black holes. And so this is because we kept the rotation, the angular momentum non-zero, whilst requiring that mass is equal to the charge, as required by supersymmetry. Therefore, these solutions will either contain naked singularities, or they can be traded for closed time curves.
This is a 1 parameter family, and is it always equal to Q, and you can dial A to any value you want?
At first you would think so. However, we will in the next slide impose that these geometries are smooth. and then this will fix for us this parameter.
So there's only one solution.
Yes.
But this requirement of smooth is not the same thing as requiring the absence of CTCs.
It's a different condition. So requiring no CTCs would actually directly force you for like J to be 0.
We'll just repeat the solution completely.
Yeah, would essentially would reduce us back to the previous case.
So there's exactly one such solution.
Let me show it in the next slide. Yeah. But so importantly, like, okay, so now we have closed time-like curves, but now we Vic rotate this saddle, and therefore there is no notion of time-like anymore, and the asymptotic time being periodic is actually what we want in Euclidean signature to apply the Gibbons-Hawking procedure. So we'll take this solution and now impose finite inverse temperature beta and impose regularity on these solutions. So smoothness on the horizon. So what does it mean to
When you
impose
say it
smoothness?
has closed time-like curves, they're closed time-like curves visible from infinity or something? Or, like ordinary curve has closed time-like curves, where they're just in a region we don't really care about. We don't think it's physical anyway.
It's not in the below the hyperbolic region?
Yeah.
Okay, but
But I'm just asking, like, what about these closed time-like curves make us say that this, like, is the singularity like visible from infinity?
Yeah, so if you didn't impose that your time is periodic,
Yeah.
the asymptotic time is periodic, you would
Yeah.
essentially have naked singularity without any horizons.
Ah, okay.
Yeah.
And
So that's why we usually don't use.
so you when you said closed time-like curves, you meant the like asymptotic time.
Yes, I mean actual asymptotic time. Yeah.
Can you go back to slides?
2 slides.
2 slides. I'm sorry.
Is this 2 or
Forwards 5 slides. And sideways.
I guess I'm just confused about the fact that it doesn't look like V has zeros in the bottom.
Oh yeah. So that's a good point. So notice that like this metric is being rewritten as this metric, so there is a change of coordinates here.
That
So
was
these
fine.
are funny coordinates because in these coordinates, each black hole is represented simply by a point in a base space. However, you can still by just zooming in onto this pole, you will still find that the area of this point is actually finite. Okay, so now we can take these solutions, these supersymmetric Riemann black hole, and we impose that it's smooth on the horizon. So what does it mean? We zoom in onto the near horizon region, go to co-rotating coordinates, and require that the resulting cigar that we have cuts off smoothly. So it's a similar story as you would usually do for a Riemann black hole. And surprisingly, what you find is that the smoothness of this geometry requires the following condition. So it requires that beta omega is equal to 2 pi r. So now this condition imposed on us by the smoothness of these supersymmetric finite temperature saddles is actually precisely the boundary condition that we would want to impose when we study the index. So recall from the first slide that when this condition is satisfied, the graph-canonical partition function will compute for us a supersymmetric index.
Sorry, I saw the beta omega is 2 pi. It's because of you require the existence of Killing spinors.
The required existence of Killing spinors is imposes on you mass equal to the charge.
Okay.
So the smoothness of this geometry imposed on us this condition, which happens to match exactly the boundary condition that we imposed. We therefore found that a smooth solution that's supersymmetric, that's at finite temperature, that satisfies the boundary conditions for the supersymmetric index. So therefore, what we can do now is simply follow the usual like Euclidean Gibbons-Hawking prescription and evaluate the on-shell action and see how these black hole solutions contribute to the index as computed from the actual gravitational pathing figure. Yeah.
So one question. So now you got a smooth Euclidean solution.
Yes.
So now you're gonna, from what you said, is do everything in Euclidean signature.
Yes.
But anyway, the solution will have a negative singularity if you allow the horizon signature. Is that right?
Yeah. If you continue to learn, it's not necessary. So you would have one of two things. You would either analytically continue to Lorentzian signature, and you would either have now a closed time-like curve, and the closed time-like curve essentially makes it so that you would like I guess the naked singularity will essentially be behind the horizon, so it's not a naked singularity. Or you would get the, or you would decompactify your time, in which case you would see the naked singularity.
So in either case, you would get something which is a Lorentzian geometry, which is not really a...
Doesn't make sense.
Canonically good one.
Right, exactly. Yeah.
But
To be clear, if beta is purely imaginary, then to the extent this geometry is anything, it is a Lorentzian geometry, right? It's not Euclidean now that we have imaginary.
It's a complex metric, yeah, but the point is that it's not Lorentzian in the sense of having like.
Could you not think of it as purely Lorentzian, just with a closed time-like curve? Like,
I mean, well, if you Vit rotate it, then you could. If you
but
decided
beta is imaginary, so like,
what's imaginary, sorry?
if beta is purely imaginary, then
Beta is not imaginary. Sorry, no. Here I think of it in terms of having angular velocity as being.
oh, sorry, yeah, sorry, beta is, yeah.
Sorry, I keep beta to be real, following the usual talking.
I guess you could keep beta to be imaginary, make omega real,
Yeah.
in which case you would have a Lorentzian
Yeah.
geometry that would have a closed time-like curve that's rotating,
Yeah.
and would still be computing this trace. Yeah.
Yes. Thank you. Okay, so we evaluate the on-shell action, and what we get is the following simple answer. So it's E2 minus beta q plus 5q squared. So there are two important things to know about this result. So first of all, this result is linear in inverse temperature beta. This is really good because this serves as like kind of a consistency check of the Gibbons-Hawking prescription. Because if the Gibbons-Hawking prescription is supposed to be computing a trace, and we are supposed to be computing a supersymmetry index, the most you can get when it comes to a temperature dependence from this expression is E2 minus beta multiplying the ground state energy in your given charge sector. So you shouldn't get any more complicated temperature dependence. And indeed, we do not. We get only this trivial. However, notice that the fact that this dependence is linear in inverse temperature beta is very non-trivial, because now what we used to evaluate this on-shell action was a finite temperature solution that actually has a non-trivial dependence on the inverse temperature beta. However, it ends up being the case that the smoothness of these solutions precisely plays out in such a way to give you only this simple dependence on beta. Secondly, yeah.
So just going back to this question, I got confused by that. I thought that it was important for you for beta to have the interpretation as the inverse of a real temperature. And
Yes, that's
when we make identifications, it's not ambiguous whether we make them on the real or the imaginary axis. So beta is like a circle on the real, it's periodically identified.
Yes,
Well,
yes.
we can choose it to be anything we like, right? So we could make it complex.
We could, but
You
then
take the limit.
we lose the interpretation of interpreting it as an inverse temperature, right?
Yeah.
Yeah, it's a complexified
Yeah,
temperature.
it's
That
not
formula
Yeah.
trace e to the minus beta 8, that formula would hold even if we took beta to
Yeah.
as long as beta has a positive real part.
We do it with a spectral form factor, for instance. We analytically continue beta.
What's not, sorry, what I'm trying to get at is that whether I identify Euclidean or Lorentzian time periodically is objectively two different things. That has nothing to do with whether I view this as a single,
Yeah.
right? And I'm trying to understand which of these things you're doing, whether you're doing them both, because it sounds like, I don't
I
know.
think you should ignore my comment and beta is real. Like,
So we're
like you
identifying-
could in principle make it happen.
For the first, yeah, it is quite different beta.
The reason, sorry, I'm not quite done. The reason I was asking is that if you were also saying that they're close time-like curves and they have to do with they're actually in the asymptotic region. That makes it sound like we are identifying Lorentzian time periodically, which is different from identifying Euclidean time periodically. And so I'm still a little bit confused.
I think for beta real, the omega needs to be complex to imaginary to satisfy beta omega is 2 pi r. You get some complex geometry that is smooth. For beta imaginary, you have omega is real and you get some real Lorentzian space-time geometry, except it has closed time-like curves because you have some finite imaginary beta.
Yeah, so in Euclidean signature, there's no problem at all. If I set beta to be real, there's no notion of closed time-like curves.
Right.
So
But again,
let's just say that that's the setup.
whether I,
Yeah.
I'm asking a discrete question, not where you want to be in a complex plane. I'm asking which identifications you make in it. Whether you make one or two in a long range
One.
axis.
Tau goes to tau plus beta. That's standard.
Good.
So going back to this, the first point was that the inverse temperature beta enters linearly in this answer. And the second important point is that what we reproduce from the on-shell action is the entropy of the extremal black hole given by HEP squared. So now, what I want to point out to you is that importantly, this answer is in particular not the area of the horizon of the black hole that we actually use to evaluate the on-shell action. What we evaluated the on-shell action with was a finite temperature supersymmetric saddle that had some non-trivial temperature dependence, and correspondingly the area of the horizon actually depends on the inverse temperature beta. However, it turns out to be the case that there is a non-trivial cancellation of beta that happens between the entropy term of the finite temperature black hole plus the beta omega j term, since we're working with a grand canonical ensemble. And this cancellation precisely plays out in a way to give you back the entropy of the corresponding extremal black hole at zero temperature. So in this way, we essentially reproduce the extremal black hole entropy without actually relying on the usual Lorentzian logic. We follow purely the Euclidean gravitational path integral, and we got the answer that would matter a prediction. And the reason why it played out in this way was because smoothness required the parameters of the solution to be precisely such that this cancellation happens.
Is there some general argument for why you get a cancellation, like the existence of a Killing spinner in the geometry or something forces everything to be linear? Like, I don't know, it feels like there should be some general explanation.
Yeah, but you mean a gravity explanation?
Yeah, like within the gravity calculation, there should be some way to see that the supersymmetry dissolution or something means that
right. So other than you can expect it from from the Gibbons-Hawking prescription, but without relying on that, I'm not aware of the argument that would make that would trivialize all of these computations.
Maybe I can make a comment, which is that the existence of a Killing spinner guarantees that n is equal to q, which in turn guarantees that the derivative of that partition function with respect to beta just pulls down a factor of q. So it guarantees that in the exponent you have something that looks like e to the minus beta q. Now, I think the part that is not guaranteed by the standard calculation is that the additional term that looks like HEP squared is the same as the extremal entropy. That's just a number that's related to. But the dependence on beta is guaranteed from the existence of a Killing spinner.
But if it's independent of beta, can't you just take the limit where beta goes to infinity and then...
Yeah, but it's not a smooth limit.
Yeah. But doesn't the geometry look like the extremal black hole in that limit? Beta really big.
Yeah, it does. In the beta going to infinity limit, you would get back the extremal. However, you cannot compute the gravitational path integral directly in the beta to infinity regime.
Yeah, but you could do it at very, very large beta, right? And then the area term is the extremal area, and the beta omega j is tiny. And
right, but for that you would still need to find at least perturbatively the solutions at some non-zero and not infinite beta, right?
Yeah, I'm just trying to understand the independence of beta, and it seems like Licker's argument, I maybe believe, tells you that it has to be linear in beta, and then it's just the question what the constant term is, and that seems...
Yeah, if you believe that constant term should automatically become the area of the extremal black hole, then it's fine. However, computing the on-shell action in the extremal case is kind of plagued by problems. In fact, Gibbons, Horowitz, and Ross use the computation of the on-shell action slightly before Strom and Jerevaffa to argue that the entropy of extremal black holes is zero.
But that was just the geometry. I feel like that's fixed by having beta be finite.
Yeah. So it's fixed by this regularization where you take beta finite.
Yeah. But if we take beta equals 10 billion, then that bottom line, the first term, it's just the area of area B2 is just pi t squared, right? Plus something time.
Oh, you
And then
mean
B2
one
and
over
Bj would basically be 0, I think. If we took, yeah. Okay.
Yeah, because J is monotonically decreasing with
Yeah,
beta,
exactly.
at
Yeah.
least at large beta. So
Yes,
it's
yes,
very
yes.
large beta.
Okay, so that was essentially the main procedure that we follow in this talk. But now, to generalize this construction to multi-centered black holes, we'll have to understand how to impose smoothness in a slightly different way. So for that, we'll analyze the potential existence of Dirac-Misner strings in this geometry. So recall that the other way of writing the supersymmetric Kerr-Newman black hole is in terms of these Israel-Wilson coordinates. And here, importantly, the object that captures the rotation of these black holes is this one form omega e, which is given by these equations. And now, these equations, after appropriately integrating them over a region of space-time, you can find that this one form field omega, similarly to like the gauge field in electromagnetism, they can actually contain the analog of Dirac strings. And in gravity, these are called Dirac-Misner strings. So these would essentially be one-dimensional regions of your space-time where your metric essentially blows up. So to make sure that the geometry is smooth, we have to make sure that this singularity that we naively see in this one form field omega is only a coordinate singularity and does not lead to any actual curvature singularities in the geometry. So it turns out that you can remove simply this Dirac string by performing a shift of the Euclidean time coordinate in the direction of the angular coordinate around this Dirac string. However, for this coordinate transformation to be valid, you have to make sure that the periodicities of the time coordinate and the angular coordinate are consistent with each other. So this imposes on you the following smoothness condition in the Israel-Wilson language. So now, if you analyze, let's say for the one black hole example of like one north pole and one south pole, this smoothness condition that we just derived, you'll find that it's actually exactly equivalent to this condition beta omega equal to 2 pi I. Now, you can think of it in the following way. For supersymmetric rotating Kerr-Newman black hole, the smoothness condition fixes essentially the angular velocity in terms of the inverse temperature beta, whereas for the Israel-Wilson way of writing the metric, the smoothness condition essentially fixed the distance in the base space between the North Pole and the South Pole, essentially by this equation. So that also tells you that the distance between the North Pole and the South Pole captures the rotation of the corresponding supersymmetric black hole. So with this, now we know how to impose directly in the Israel-Wilson coordinate the smoothness condition. We can therefore impose the smoothness condition in the general multi-centered case. It's a very simple exercise because you just get a single smoothness condition for each pole in the geometry. So this will lead to some non-trivial constraint on the possible positions in the base space of these black holes. Importantly, let me point out that now in the Israel-Wilson way of writing the metric, the black hole is represented by, as we said earlier, North Pole and the South Pole, and they can be thought of as connected by this removable Dirac-Misner string in the geometry. And this removable Dirac-Misner string essentially captures the horizon of the supersymmetric rotating black hole. So the general geometry for this multi-centered case is going to look something like this. And we can now evaluate their punctual action as well. And what we'll find is, again, the answer that's consistent with the index, where these A's are essentially related to the black hole charges of the individual Kerr-Newman black holes.
Do you have to consider the possibility of having this drag strain between every pairwise sense of multi-centered?
No, you're gonna find that because of the smoothness, they will only be connecting pairwise.
So what if it's like an odd number of centers?
If it would be an odd number of centers, then you would not get. This would be like I don't know if you're familiar with the Taubnat geometry, but this would be the example of the geometry you would get. You would essentially have a runaway Dirac-Misner string that goes to infinity, and therefore correspondingly asymptotic infinity will not be asymptotically flat anymore. So you can actually, if you're familiar with it, you can actually think of the North Pole as being like a nut charge and the South Pole carrying an anti-nut charge. So then these together they can form a black hole in this case. Okay, so this is the simple strategy that we followed before we move on to the generalization of these geometries. So we started with external Nordstrom black hole, which was represented in the Majorna drop control language by a single second-order pole in the base space. Now, keeping the supersymmetry condition intact and turning on the temperature, we essentially turn on allow these black holes to rotate. So this essentially splits the single second-order pole into two simple poles in the geometries that are now connected by the Dirac-Meissner string, which captures the rotation. So now we'll follow this simple picture to generalize a family of more complicated solutions in the n equals to supergravity coupled to vector multiplets. So here let me very briefly introduce some notation and what's the bosonic part of the theory that we're studying. So it's the bosonic part of the theory is described by the following action. Here, TAs denote the complex scalar fields. There is NV of them. These complex scalar fields are now coupled to NV plus 1 gauge fields through this scalar-dependent matrix Nij. Because we have NV plus 1 gauge fields in this theory, correspondingly the charges are going to be now vectors of 2NV plus 2 charges, where P's denote the magnetic charges and Q's denote the electric charges. There exists a natural action of the electric-magnetic duality in this theory, which is captured by the symplectic transformations on these vectors. And correspondingly, there is a duality invariant product, which will just this bracket will essentially appear on some subsequent slides, which is simply given by this simple expression in terms of the charge, in terms of these of the corresponding components of these charges. And lastly, there's also these NV scalar fields. It's useful to repackage them into essentially a vector that transforms naturally under these duality transformations, and we'll denote it as omega of t because of the standard notation in the literature. So please keep in mind that when it's omega of t, it's not the angular velocity actually, just to avoid confusions. So now, in this theory, the most general family of solutions is again described by the so-called now Bates-Denef solutions, but they again have a very similar ansatz. They are now described in terms of the whole vector of harmonic functions, which again has 2NV plus 2 components, a one-form field, which is determined by similar equations as before, and a rather complicated object that's called the entropy function. And this object is essentially just a homogeneous function of the components of this harmonic function. So essentially you can however find, just for some intuition, that if you, for example, for the single black hole case with a single pole, if you try to compute the area of the corresponding extremal black hole, it's simply going to be given by this entropy function evaluated on the corresponding monopole charge of this black hole, as is given here. Now, following kind of the same structure as before, supersymmetry instead of just mass equal to the charge, now it actually invokes the so-called generalized attractor equations, whose role is essentially to fix the values of the scalars in the geometry in terms of the harmonic function stage. These generalized attractor equations are essentially generalizations of the famous attractor equations, which essentially tell you that in the extremal geometry, if you zoom in onto the horizon of an extremal black hole, you'll find that the values of the scalar fields get attracted to a value that's independent of the asymptotic boundary conditions for the scalar fields. This was, back in the day, very important for the interpretation of the black hole entropy for the interpretation of the area of the extremal horizon as the black hole entropy, as naturally if this was not the case, if this was not satisfied, we would find that the area of the horizon actually can depend on the asymptotic values of the scalar fields continuously, and this would be problematic from the perspective of interpreting it as a black hole entropy of the corresponding black hole. So the original attractor mechanism is what saves us from this. So now we take these solutions, we derotate, and we follow our single picture. So now the single black hole, which had second order poles, we split it into two simple poles, which will now have mu charges, the little gamma north and little gamma south, and they will now have correspondingly the positions x north and x south. So after derotation, this is the form of the metric, and the harmonic function now actually contains two poles describing this situation. We want to ensure that the total charge asymptotically of the solution is still the same, is still equal to the monopole charge, and we now want to impose smoothness of this solution. So to impose smoothness, we first impose the no conical singularities in the geometry, so it's the same story as with the supersymmetric rotating kernel black hole, and as in the Israeli-Wilson case, this will fix for us the distance between the North Pole and the South Pole. On the other hand, something that was implicit in the Israel-Wilson solution, but now we have to impose it by hand, is we want to make sure that this geometry cups off smoothly, but at some finite distance in the bulk. So we don't want any infinitely long horizon in the growth in the near horizon region. Imposing this will fix for us actually the exact difference between these new charges that we introduced. So with these two conditions, this will uniquely determine for us the charges of the corresponding new poles that we introduce in the geometry.
Sorry, this looks a little bit confusing. So you require some quantity to be, say, smaller than infinity, but you use this inequality to get an equation to fix gamma n minus gamma x.
Oh yes, because the point is that you can simply say that, think of it this way: you have this this entropy function sigma, which is a function of these harmonic functions, right? So you evaluate it and then you zoom in onto some poles, right? So as you zoom in onto some poles, the only thing that you want to impose is that there is no second order poles, because as I pointed out in the beginning, the second order poles in the Majumdar petrometric is what would capture for you the infinitely long throat. So just requiring that, it turns out that it will fix for you the values through supersymmetry condition as well, fix for you the values of these charges.
Question?
Yeah.
I'm confused about how the finite temperature is splitting the black hole. Is this different than if you took the solution in Lorentzian signature to the harmonic function that corresponded to two centers, and then just did the continuation of that?
Yeah, that is different, because so that's why we kind of, to follow the procedure, right? We split it by hand, we construct the solution, and then you find that this is a solution that's smooth, and that in the zero temperature limit it reduces to the extremal solution. However, if you started with a valid Lorentzian configuration with two monopole charges, then what you would find is you would find that it's a completely different situation, because you're gonna find that these charges have to be complex. So there's actually a genuinely complex saddle that contributes to the index.
So if I wanted to impose regularity on the two-center solution, it would be different conditions.
Yes, on a two black hole solution.
Yeah.
So the important thing is that notice that because there is this direct Milton string here, you cannot interpret actually gamma north and gamma south as monopole charges, because there's no actual two-sphere that can enclose them. So because of them, only this has the interpretation of the monopole charge, but these ones are essentially just the coefficients that enter the pole fields. So just briefly, as before, we impose the no-conical singularities. This imposes the new sort of regularity conditions, and then finite front in the horizon, that corresponds to requiring that we don't have second order poles. We still require that we still retain first order poles. And this turns out to require you to work with complexified charges, and these complexified charges then through the attractor equations can actually be uniquely fixed in terms of the monopole charges of the corresponding black hole. So with this, we turned on the temperature, was keeping the supersymmetry, and then this we introduced in this way new parameters into the solution. But now, after introducing these new parameters, we impose regularity on the solution, which fixed uniquely all of the new parameters. So then we can follow the same procedure as before, and we can evaluate the onshore action of these solutions, and we again find the answer consistent with supersymmetric index. Here, what I want to point out though is that now there are two regularity conditions. One was the smoothness, the other one was the fact that the geometry caps off at some finite distance. And you actually have to use both to get back the extremal entropy. So you would only land as far as here if you didn't impose the geometry capping off at the finite distance. However, if you insert now these values of these charges, then you're gonna get back the extremal black hole entropy. So again, some magical cancellation happens here, which allows us to reproduce this extremal black hole entropy. So with this, one can now repeat this this procedure for a multi-center black hole in this supergravity theories, and we again reproduce now a sum over extremal entropies of the individual black holes, together with obtaining this linear dependence on the inverse temperature vector. So now that we've understood how these multi-centered black holes contribute to the index, what we can do is we can analyze the space of these solutions, which is something that we're interested in from the perspective of the gravitational path integral. The reason why we're interested in that is because this particular theory in equals to supergravity in 4 dimensions has a very clean embedding in string theory, and therefore from the perspective of testing the gravitational path integral, it would be very useful for us to understand exactly the space of these saddles, because then we can try to reproduce known microscopic results from string theory using the gravitational path integral that we develop here, and the corresponding evaluation of that integral on these new saddles. So now, to recap, let me start with recapping the old zero temperature story. So, the new thing that happens when you couple Einstein-Maxwell theory to scalars, which come from these vector multiplets, is that now your black holes can form band states. So now, again, we have two centers here, but now you can, in this slide, you can think of each of these centers as actually a genuine extremal black hole. And now, what happens is that the geometry that involves two such black holes will only be free of closed time-like curves if the distance between these two black holes is uniquely fixed in terms of the monopole charges of these black holes and the asymptotic scalar moduli, which is captured by this parameter little h.
Sorry, maybe I missed this. Like, why do they have to form band states?
Yeah, they have to form band states because you just consider, in this situation, you consider the Lorentzian solution that's supersymmetric that I described on this first slide of this n equals to supergravity. And now you analyze, does this geometry is this geometry free of naked singularities? And then you're going to find that, it's only going to be free of naked singularities or equivalently closed time-like curves if the following so-called integrability condition is satisfied. And this condition fixes for you the distance. But now these are Lorentzian solutions now.
Maybe a more physical picture is that in Majumdar-Papapetru, what happens is that gravity exactly cancels the electromagnetic repulsion, whatever the distance, because they both have the same type of fallout.
But this is still the zero temperature.
Then
Yeah,
we
yeah,
have
yeah,
a
so-
very long throat for each one of them. Right?
Yeah, so these ones still have an infinitely long throat. It's only a finite distance in base space.
Ah, okay.
But what happens here is that there is because of the scalar interaction, because of interactions mediated by scalars, there is an effective potential which only has a minimum at one location. So instead of the gravitational force canceling the electromagnetic force, this addition of a scalar force only leads to one minimum instead of a continuous set of states.
So now what happens with these bound states is that as you now tune the values of the asymptotic scalar fields, you can actually approach the region where the denominator vanishes and then changes sign. So essentially what happens is the bound state suddenly has to be separated by an infinite distance, and then afterwards it has to be separated by a negative distance. So in other words, you lose this solution, and this is usually interpreted as losing states from your Hilbert space. So this is known as the so-called wall crossing phenomenon, in which your supersymmetric index can actually discretely jump across certain walls of marginal stability as you tune the values of the scalar moduli. And correspondingly, this region where this denominator vanishes is referred to as wall of marginal stability.
Sorry, just to make sure, like, how do you tune the scalar moduli, like by changing the superpotential or what?
You just you just change literally the boundary conditions for the scalar field of infinity. Like the values. So now our goal is to understand how this wall crossing phenomenon appears from the perspective of the finite temperature packet control. So recall that now after turning on the temperature with our new solutions, we now each black hole is represented now by a north pole and a south pole, and correspondingly what previously was this condition for no closed timeline curves is now upgraded to the smoothness condition in the geometry. So you can think of this smoothness condition as a set of equations that essentially constrains the possible positions of this black hole in the base space. Now it turns out that for just the bound state, which is the two black holes, you can actually explicitly solve these equations for the distances. So
I'm pretty too naive, but when you turn on temperature, why still you can choose scalar? Because of finite temperature, the scalar, I think, get the mass and the rate.
So the way I think about it is that I'm computing some partition function from using the gravitational packet integral, and asymptotically I can impose some boundary conditions for the scalar fields at asymptotic infinity.
Even if it's not a flat.
Yes.
Yeah, you can certainly do that just by now.
Yeah, just by hand I change the boundary conditions for the scalar fields. Does that make sense?
Yeah,
I mean, you have to.
too naive anyway, but the scalar will usually get.
But not if you compute an index, actually. So the thermal mass, when you compute an index, happens to be 0.
Ah, so why is that suggested?
Well, it's because when you do the dimension on the field theory side, so this has nothing to do with gravity, but if you do the dimensional reduction with index boundary conditions, the theory that you obtain in one lower dimensions can still be a massless theory. So there's modes in the quantization of scalars that even though you had naively your theory would be gapped by the scale of the thermal circle, because of the change of boundary conditions, it just happens that the thermal mass, even in interacting theories, is 0.
Okay.
So now these regularity conditions can be solved explicitly for the case of two black holes. So what you find is it's going to be this schematic set of solutions. You don't need to pay attention to the details of them, but the only thing that I want to point out is that first of all you can explicitly find these solutions for the distances, and second of all we can fix all of the distances except for one. So we are actually left with one free parameter now after turning on the temperature. So what this means is that what was previously like this essentially a moduli space that was a point, which was this unique solution for the bound state, for the bound state, now got its own continuous moduli space that's parameterized by this distance x1 minus x2, which we take here to be essentially the distance between the north poles of these black holes. So with this, we can now ask, okay, are any of these configurations for like any values of x12 valid for the gravitational path integral? So first of all, what we need to impose further is the fact that the distances are actually positive. So this will lead to some restrictions of the moduli space. And second of all, what we need to impose is the fact that these distances that we found, the values of these distances, can actually be embedded in R3 as distances between points, right? So that's like essentially, we're just simply saying you need to impose triangle inequalities as well, but also for this more general, simplex that we essentially have, which is like the tetrahedron here. You want to impose essentially that the volumes of these simplices that you study, computed in terms of distances, are non-negative. So that as long as you ensure that, you can essentially, the Kylie-Menger condition tells you that if you ensure that, which is captured by this Kylie-Menger determinant, then you can actually embed these distances as genuine distances between points in R3. So yeah, this is this Kylie-Menger condition. So now what we simply do to analyze this moduli space is we pick a specific charge configuration and we analyze how does this condition play out in a specific example. So if you plot this volume of the tetrahedron in terms of the distance x12 that we have, you're gonna find that actually for most of the values of the moduli, you don't actually get the valid configuration. So we get some distances that don't actually make sense as distances between points. However, if you zoom in a little bit onto this tiny region, you find this tiny moduli space here. And now this tiny moduli space is like essentially the moduli space where the volume of the tetrahedron computed in terms of the distances is actually positive, so that's good. And we can further check that the triangle inequalities for any subset of points are also satisfied. So therefore, we found a region of the moduli space in terms of x12. Where these distances that we found actually make sense. So therefore we found the solutions to these regularity conditions. Yes?
So would you call the zeros of this like shape the ball of marginal stability?
No, that's a different thing. So this is like because the words of marginal stability, so I'm kind of overusing the language here. I'm using the word moduli for two types of things. There's moduli in the sense of space of solutions for given boundary conditions, right? And this is the moduli that is described by this x12. And there is separately a moduli which is essentially the boundary conditions for the scalar fields. That's actually changing the boundary conditions of asymptotic infinity. And usually wall of marginal stability is what you would refer to as the one coming from the scalars. Okay, so now after we found this moduli space and we ensure that it makes sense, we can ask what are the black hole configurations that are contained in this moduli space. So here we plot, I plotted a few examples. So starting, so just to describe it a bit, these arrows essentially represent the distances between the south pole and the north pole, so they point from south pole to the north pole, and the direction and the magnitude of these arrows can be thought of as capturing the rotation of these black holes. So now you'll find that the left edge of your moduli space is essentially represented by two arrows that are like parallel, so that means two black holes that are actually rotating in the same direction. Now as you move from the left edge to the right edge, one of these arrows is going to start rotating with respect to the other. In the middle of the moduli space, you're going to find that these arrows are actually perpendicular. And then at the right edge of the moduli space, you're going to find that you have anti-parallel black holes. So like anti-parallel black holes in the sense of like the rotation is in the opposite directions. Importantly, these black holes actually, like, these arrows rotate between each other in like parallel 2D planes, so they never develop like some component that would go in the direction of the other black hole. You might ask, why is it a rotation only by pi? Why not by like a full circle? So the reason is that we actually missed something. We missed the fact that, like, so far we're describing the space of solutions in terms of distances. But now to go from distances to Cartesian coordinates, you have to also like solve for these coordinates. So you're gonna find that you actually get two families of solutions. And the other family of solutions is gonna be exactly the same moduli space, but with reflected arrow in the other direction. And therefore, the full moduli space of these finite temperature solutions is actually given by the full circle. So we started with a moduli space at 0 temperature that was simply a point, but now after turning on the temperature, this moduli space developed into like a topologically an S1 moduli space, whose size is now dependent on the inverse temperature data. So now let me focus on an important part of this plot, which was maybe not that visible, but there is a gray line there, and this gray line is important. So the gray line is essentially a plotted value of the distance between the North Pole and between the North Poles, equal exactly to the original 0 temperature distance between the constants. And just like a specific value of x12. And now you can see that like this moduli space of solutions kind of nicely lies on this gray line. What you're gonna find from this is that like a natural consistency condition that has to be satisfied, and indeed is satisfied, which is that if you now take a 0 temperature limit, you should reproduce the 0 temperature moduli space. And indeed that's what you find. You see that this moduli space collapses onto this 0 temperature solution. But more importantly, because this moduli space is now essentially kind of anchored on the 0 temperature moduli space, you can immediately see how the wall crossing happens at finite temperature. Because you can effectively think of it as the finite temperature moduli space as being carried around by the 0 temperature moduli space. So correspondingly, as you now progressively approach the wall of marginal stability, what you're going to find is the full moduli space in terms of x12 is going to move to larger and larger values of the distances, and then correspondingly, when you hit the wall of marginal stability, this full moduli space will go to infinite distances and then will jump to negative distances. So in this way, you're gonna lose the full moduli space of solutions at finite temperature, and that's how wall crossing essentially happens from the perspective of the gravitational path integral. Okay, so now I have the part about the indices of 5D black strings, but we should.
There were other questions. If you want to go another 5 minutes, and
okay,
then close, and then everyone can leave, and they.
Okay. Yeah, I think I can finish it like. Okay, so now what I want to discuss is slightly change gears and show you how these new index saddles can be used to actually construct the index saddles in other theories as well. So for that, let me recap briefly the kind of string theory origin of the theory that we're studying. So we're studying n equals to supergravity. This supergravity that we're studying can precisely be obtained by starting with type 2a supergravity in 10 dimensions and compactifying on a Calabi-Yau freefold. So Calabi-Yau freefold is like this compact manifold that has 6 dimensions. So that's why from 10 you end up in 4 dimensions. Now, type 2a supergravity can also be obtained from 11-dimensional supergravity, which is conjectured to be the low energy effective theory of M theory, by compactifying this 11-dimensional supergravity on some spatial circle. So now you could imagine going in this diagram in the opposite direction, where you would start from this 11-dimensional supergravity, compactify on the Calabi-Yau freefold, and you get 5-dimensional supergravity, which is then related for a compactification to a 4-dimensional supergravity. What this means is that we can essentially, through this connection, immediately write down the saddles of the supersymmetric indices in 5-dimensional supergravity as well. So before doing that, for some specific example, let me recap for you a particularly interesting example that we could study, which is the one related to a black string. So here, in M theory, what you can consider is an M5 brane, so that's like an analog of a D brane, but in M theory, which can be wrapped on a fourth cycle of a Calabi-Yau manifold. What you're gonna end up with after compactifying is a 1 + 1 dimensional object in 5-dimensional spacetime. Now, using the usual ADS-CFT logic, this object can either be viewed from the supergravity perspective as a black string with the near horizon region of given by ADS 3×2, or it can also be described for a low energy effective theory that lives on the world volume of these membranes. And this is known as the MSW 2D-CFT. Gabriela, you should listen now.
You literally have your paper open here.
Okay. So now with this, the corresponding ADS-CFT conjecture in this setup relates now this 2D-dimensional supersymmetric conformal field theory to M theory living on the ADS 3×2 Calabi-Yau pattern. So this is like the kind of the analog of what you would usually say about type 2D string theory living on ADS 5×5. And now for this MSW CFT, there's actually a natural CFT prediction for the index that has been derived back in the day. And it's simply given by this expression, where these gammas are essentially these, in the 4-dimensional notation, these are the charges of the corresponding black hole. And importantly, this index actually matches the horizon area of the corresponding extremal black string. So that's the usual kind of old like Lorentzian logic, where you compare the index to the horizon area of the corresponding extremal black hole.
Black string.
Black string, thank you. So now, what we can do is we now take this setup and we simply uplift our index saddles to 5 dimensions. So there are 2 ways in which we can now compute the index. The first way corresponds simply to taking this 4-dimensional black hole and uplifting it to 5 dimensions without taking any limits. The index remains invariant throughout, and so we already get the answer. And this essentially the index with R3 crosses 1 crosses 1 asymptotics is captured essentially by a black string that wraps this M theory circle and rotates now in 2 directions. It's going to rotate kind of in a 5 direction, which is hard to draw here, and it also rotates along the M theory circle. We can also go a step further, and we can take the decoupling limit in which we zoom in onto the near horizon region. What we're going to end up with is this BTZ black hole cross S2. So we're going to end up with a finite temperature solution in 3D gravity that now computes the index with ADS 3×2 asymptotics. Now, as I pointed out, the supersymmetric index remains essentially the same throughout all of these steps, and so therefore from this we have essentially found the corresponding index saddle for MSW CFT, which was actually previously unknown. But what I also wanted to point out to you is this method of computing the index, because in particular what this also means is that the supersymmetric index computed with this asymptotics without taking any decoupling limits actually reproduces the index of the MSW CFT. So what this essentially illustrates for you is the usefulness of the Gibbons-Hawking prescription in the asymptotically flat space, as we essentially expect that the construction that we presented here would also work for different other degree configurations. So what you could try to do now, for example, is you could ask yourself, okay, can I compute the supersymmetric index of n equals 4 super Young mills directly from a 10-dimensional asymptotically flat gravitational path integral without ever taking any decoupling limit where I would be zooming in onto the near horizon regions. Okay, so with this I'm done, and yeah, let me, if you would then summary here. Oh, actually, okay, so this is the summary. Is there some future directions? Great, thank you.
Questions for you?
What's the picture of losing saddles? Like from the scalar potential point of view, Luca was explaining that like the existence of the scalar potential and its minimum is something like how the distance between the black holes.
Yeah, it's essential.
Yeah. So how does say the bound state go away because?
Yeah. Essentially, the minimum of the potential goes to infinity, and you lose the minimum, so you cannot form a bound state.
So this is by dialing the boundary conditions of the.
Yes.
Okay.
Essentially, your potential becomes unstable. There's no, you get a potential that doesn't have any minima anymore.
So do you know what would be the theory? Like here you computed some index of some 2D CFT by using some 4-dimensional gravity in flat space. And so in the case of n equal 4 supreme meals, you said something 10-dimensional, but it's not entirely clear to me why it should be 10-dimensional, right? Like if you only knew about the CFT, we know about n equal 4 supreme meals, and we know about its ADS dual. How do you from that find or guess a flat space black hole that gives you the same?
No, what you simply do is you take a stack of 3 branes, right? You take like your starting point of the usual ADS-CFT construction, and you just don't take the decoupling limit, but instead like ask yourself, okay, what can I do to like now consider like a finite temperature solution that would be super symmetric, and then you can say, oh, now I'm computing a 10-dimensional asymptotically flat gravitational index, and then for a specific saddle that would correspond to this particular stack of the 3 branes, you should essentially reproduce the supersymmetric index of supreme index without ever having to zoom in onto the ADS5 process 5 region.
Without the ADS5 process 5 region even existing.
Exactly.
Like it's just purely flat space, a flat space solution. It has nothing to do with ADS.
But this is particularly nice because a nice fact is that in 11 dimensions, the supergravity that you can write down is essentially unique. So the nicest way to do things would be to just directly compute everything in 11 dimensions, and you should be able to reproduce all sorts of indices by like focusing on specific samples.
So you told us about how these saddles are related to the solutions in the Lorentzian signature, but do we know whether or not these are all the saddles that contribute to the Euclidean?
So here I was, it's pretty clear that these are not going to be like all the saddles, right? You can also have some orbital saddles and so on. So we're focusing on the leading saddles that are essentially like correspond to like the black hole saddles.
Leading, I'm sorry, leading.
Sorry?
Leading how?
Leading in the sense of having like the leading contribution like from the action. Yeah. So in particular, like for the example that I was saying that like an example where you want to test the gravitational driving integral. So if like previously like Luca Simon and Joaquin computed directly this index of n equals 8 supergravity, but I was still using the logic of like the kind of near horizon region. So if you manage to first like generalize that to asymptotically flat space, then you could go to like n equals 4 supergravity, and there you would know that there would be more than a single saddle like contributing. But essentially, like for each like kind of black hole saddle that would contribute, which would be like similar to this, like for example, a bunch of different multi-center black hole saddles with different charge configurations that would contribute, you could essentially run this story. This essentially tells you what are these actual saddles that are contributing and that are computing for you this index.
Any questions for you?
Do you think this is possible also plus because you're thinking about supersymmetric black hole. This last thing about like doing a computation for a black hole in flat space or some stack of droids in flat space and then getting the entropy of some CFD.
Yes, essentially because you expect the index to be temperature independent,
Yeah.
right? So because the index is temperature independent, you can kind of avoid this decoupling here.
Can you explain again the new saddle that you found to match onto the index for that theory?
The 3D saddle?
You said that you were able to use this method. Wait, one sec.
This one.
Yeah, to find a previous. So what is this new saddle you were able to find?
Yeah. So this particular equation refers to like this is the CFT answer. So like in the actual like you would take the decoupling limit, you would find the low energy effective theory, you would compute the index there. It gives you some answer. And this answer matches to the answer that you would compute from gravity from the 5-dimensional perspective. So not from the 5-dimensional perspective, but also asymptotically flat. So this is this saddle. Like like this. So this is like a black string saddle that essentially rotates in 2 different directions with imaginary value of angular velocity. And it essentially you can think of it as like a black string that wraps this additional S1 that you have because of M theory. And this black string has a S1 cross S2 horizon. Essentially the point is that if you evaluate this on-shell action, you're going to end up with the answer that exactly reproduces the answer of the MSW CFT, even though you haven't really decoupled the theory from asymptotically flat space.
If there are no more questions, let's thank Gavin.